Hello there, and welcome to the series Introduction to Google Colab for Research. I am Renato, the instructor for these tutorials, and the topic of today is how to compile C and C++ to WebAssembly and run C and C++ apps on the web. So WebAssembly is a binary instruction format for a stack-based virtual machine and is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. So the WASM, as it's called, stack machine, is designed to be encoded in a size and load time efficient binary format. WebAssembly aims to execute at native speed by taking advantage of common hardware capabilities available on different platforms. To use the WebAssembly to compile C and C++ code to WebAssembly, we're going to use a toolchain, compiler toolchain called Emscripten. So Emscripten is a complete compiler toolchain to WebAssembly using LLVM with a special focus on speed, size, and the web platform. So LLVM is a collection of modular and reusable compiler and toolchain technologies, and despite its name, it has very little to do with traditional virtual machine. So the name LLVM is not an acronym, but it's the full name of the project. We'll use Emscripten to compile your existing projects written in C and C++ to WebAssembly, and then you can use C and C++ functions running directly on the web browser. And we will start this tutorial by installing Emscripten. So here at emscripten.org, we can go here to getting started. There will be download and install with the installation instructions using the EM SDK. So first, what we're going to do is we're going to clone from the Git repository. Clone. Now we will cd into the clone directory. We've showed how to use this magic commands, magic cells, how to git clone in previous tutorials, so you can take a look at our playlist to see, want to learn more about these topics. So then we need to install the latest SDK tools. Then we also need to activate. We make the latest SDK active for the user. And it tells us that it's convenient to access the EM SDK tools from the command line, that we should adding this to your path. So this can be done if you run this shell. Unfortunately, it doesn't really work in Google Colab, so we can do this step. It tells that it's adding the directories to the path. However, so if we try to run, for example, this EM++, it will not find this command. And this command is located here, this path. So if we replace like this, EM++, now we see that it finds this file. Just gives an error because we didn't put any input files for compiler. But we see that this script didn't really work. So what we need to do is we need to use the full path of the compiler. We will start with a simple hello world example, and then we will move on to slightly more complex example where we will use the add integers that we showed in our previous tutorial. That's how to use C and C++ code inside Google Colab. You'll find at our playlist. But first, let's write a file called hello.cpp. Inside this file, we will include IOStream. There is our main function, and then we are simply using the stdcout with hello world, and this will be what we want to do is to display hello world. When we write this file, you see that appears here. We have this hello cpp file. If you go here to the Emscripten.org, and there you'll see Emscripten tutorial, and this will give you the first steps how to use Emscripten. And here, for example, there is a running hello world.c. So here we have our C file. Here we would build, for example, the JavaScript version using this emcc. But what we are going to do is we are going to use our C++ example. So as I mentioned before, we need the full path to the em++. Then we are using here em++ hello cpp, and here when we specify that WASM equals to 1, it means that we want as an output also a WASM output. So let's run this. Now we see here at our content that we have our hello cpp that was created up here with the right file. But now we have a hello HTML, hello JS, and a hello WASM. So it generates a hello HTML for us, and now we can start an HTTP server, and then it will start this HTTP server. For example, we can use Python and start it on localhost. We can use PyNgrok to tunnel like we've done many times before, so you can check previous tutorials if you're not sure how to use PyNgrok. And when we will access, so it already generates this HTML file for us, and you'll see that there is this Emscripten logos and everything, but you can also create your own HTML file. You can also do many different things, combining JavaScript and using functions. So, but first we start very simple. We have this hello world. So when we start this HTTP server and we will access this hello HTML, there should be printed hello world. So let's do it. First, I will install PyNgrok so we can tunnel the HTTP to. Here we are configuring ngrok and PyNgrok to use your authorization token. You'll need a ngrok account there. There's a free account with certain limitations, but you can still use for research and small experiments. Here you would put your authorization token that you get from the dashboard ngrok.com.auth, and now you can already tunnel HTTP or TCP. There you can check the ngrok documentation to see how you want to use it. So we will use port 13,000, connect to port 13,000. So it's been tunneling localhost 13,000. So if we run a Python HTTP server port 13,000, it's serving HTTP at localhost port 13,000, but localhost port 13,000 is being tunneled to this URL here. Now if we click to this URL here, we have our directory listing. That is what is here in the content. we click on the hello HTML, we have our Emscripten, and there is this hello world here. So this is a template use, but you can also create your own HTML page, and we're going to do this next. So we can stop our server. And here we can view our PyNgrok tunneling. So we are clean now. Now we will go back to our tutorial number 11, running C and C++ code, and we'll use the same example that we will add two numbers. So first we need to write a file, add the file. So write file, add h, we use pragma ones, and then so here we have the function prototype. So int add int x, int y, int x, y. So now here we have our add header. Now we will write file for the add.cpp, and we will just include the header and have this function that will return x plus y. So we include add.h. Here we have int add int x, int y, and it will return x plus y, just like we have here. And then in our main file we will include iostream, we will include header add, and you just print the std cout, the sum of a number x and a number y is, and then we call this function with the two numbers, and it should be it. So let's do it. Write file, main pp, include stream, include add h, main std cout is sum of, let's say 27 plus 69 is, then we have here our add 27 and 69, return 0, and we have our main function. So here we have our add cpp, our add h, and our main. So what we need to do is the same. We need to compile for WebAssembly. So here we are calling the em++ main cpp, add cpp. This will generate our WASM file, and this we are compiling. So now here we have our add WASM, add.js. Now we will write this HTML file. So here what we're doing is just we're loading this add.js, and this will load the module and run the main, and it will display in the console. So let's run. Now we will tunnel HTTP localhost port 13,000 using PyNgrok. We will start our HTTP server. And now when you go here, we have our WebAssembly example. When you go to the console tools and hit the sum of 27 plus 69 is 96. So we have here on our C++ function here. You're displaying this in the console. We will now start following an excellent tutorial provided by the Netherlands eScience Center, and you'll find here at blog.esciencecenter.nl/using C in a web app with WebAssembly. Here's the link. So it's using C++ in a web app with WebAssembly. It's a very complete and good tutorial. And what we're going to do is we will try to find the root of a mathematical function. So this is the function here. And we are going to use Newton's method to solve this mathematical function. We will implement Newton's method using C++, and then we will compile to WebAssembly, and then we will run in the browser. So Newton's method, it's a very important method used in many different applications. So for example, it's also found in minimization and maximization problems, solving transcendental equations, obtaining zeros of functions, and we are going to use this method using successive approximations to find the root of one equation. So basically we are defining our problem, which is the equation and its derivative, because Newton's method uses the function at a certain point divided by the derivative of the function at some point where x1 equals to x0 minus the division between the function x0 by the derivative of x0. So here you will find the C++ code. So we are defining our equations, so our header file where we will have our equation and the derivative, and here we have the function 2 times x to the power of 3 minus 4 times x to the power of 2 plus 6. And here we have the derivative, which is 6 times x squared minus 8x. And here we see also it's 2 times x to the power of 3 minus 4 squared plus 6. So it's the same equation, and what we're doing, we are defining here a file called problem HTTP, our header file, and our problem CPP. So what I'm doing, I'm just copying using write file. So here we have our problem HTTP, here we have our problem CPP. Now we are going to implement this Newton-Raphson method. The Newton's method is also known as the Newton-Raphson method, named after Isaac Newton and Joseph Raphson. And here we have this header, we have our class, and then we will have a method called solve. We will use an initial guess, and also we need a tolerance. So usually we will iterate using the Newton's method, and when we have a value that is above the tolerance, we will stop, and we can achieve quite high accuracy using this method and successive approximation. And it's also very important to have a good initial guess. So we have a good initial guess, we can converge to the solution faster. If we have a very bad initial guess, sometimes we cannot even find any solution. So here we have our header file, and here we will implement this Newton-Raphson. So we will define a constructor, takes tolerance as an argument, and here we have a solve method. And the solve method takes the initial guess as an argument, and we will have this delta x. Here we will have a do while loop, what we do here, the delta x is the equation divided by the derivative of this part here. Then we update x, so x equals to x minus delta x, and when the absolute value of delta x is greater or equal to the tolerance, we'll stop, and then we will return x. So here we have then our header file for the Newton-Raphson class. Here we have our Newton-Raphson class, and we have our solve method, just as I described. Now we just will put everything together and test. So here's our main function, where we'll have an initial guess equals to -4. Our tolerance is 0.001. Then we have here our Newton-Raphson tolerance. Then root is our Newton-Raphson. We solve with the initial guess, and then we will display to print the function rule is approximately at equals to, and it will give us the value. So we see here that the root is equals to -1. Here we will compile just for testing. We don't need this to use WebAssembly, but we want to test our functions. So if you've seen our tutorials before, we have a special tutorial that is using C and C++ inside the Google Colab environment. There are other ways we can also do this, and I'm using this. I'll leave a link to this tutorial later. We also have a tutorial about the Newton's method at an optimization class from the UMNL University of Technology. If I'm not mistaken, is in multi-rate signal processing or in advanced digital signal processing, which I also offer tutorials, and you can find in my YouTube channel that I'll leave also a link. So to compile, we can run this program, and we see that the function root is approximately at x equals to -1, which we have seen also from here. Now what we are going to do is we are going to create some bindings using the Emscripten. So Embind is used to bind C++ functions and classes to JavaScript so that the compiled code can be used in a, let's call it a natural way, by normal JavaScript. Embind also supports calling JavaScript classes from C++. And here you have a quick example to use this Emscripten bindings block to expose to C++ function to JavaScript, and we will, like they are explaining here, there will be this binding. We can use our Newton code from JavaScript. We define this binding file here. So we include this Emscripten bind.h. Also include our Newton-Raphson header file using namespace Emscripten, and then Emscripten bindings, Newton-Raphson class, Newton-Raphson constructor, and there is the function called solve. Here a reference to Newton-Raphson solve is here. Solve. Here we have this float, the tolerance. And you can read more here at the emscripten.org/docs. There will be this documentation about Embind with some examples how you can use as well. So after we have these bindings, we can compile to our WebAssembly. So we are using this command here to compile. So we already downloaded the script and we've been doing this before. Compile, we will generate a module called the new Newton-Raphson WASM and a JavaScript file. Here we have our Newton-Raphson.wasm and our JavaScript file. And then we will also create our own HTML file. I explained before in this tutorial that you can generate a template using a template HTML, but you can also create, and this is what we're doing here next. So we have this script, the Newton-Raphson JavaScript that you use to load the WebAssembly module. Then we create a div where we will write the function root is approximately at x equal, and here we have a span with an ID. We will use this ID down here after we calculated the root. We use document get element by ID, so we get this element, and then we will change here to include the root value. Here we wait for the module to initialize, create module, then the Newton-Raphson. We put some hard-coded input values, initial guess, the tolerance. Here we create our new Newton-Raphson, and then we use the Newton-Raphson.solve, the initial guess, and we have our root. This is in the script part. Now we have our index.html, which is also here, and we can start an HTTP server using Python, for example. Then we will tunnel using PyNgrok, like we've done many times, and then we will access this index.html, and there should be written function root is approximately at, and we should have our answer, which is the same we have here. So let's do this. Here PyNgrok, once again you need to put your authorization token. Here we will connect, start tunneling. Now we will start our HTTP server. When we click here, it loads our index file, and here we have the function root is approximately at x equals to -1. So this is a very interesting way we used our function in C++. We have a class with a solve method. We can access it from JavaScript. We use these bindings here, and we can have our own HTML index page. When we go to the tunneled URL, we have our result here.